there could be a wormhole connecting that particle with the particle that is in the radiation that is escaping from the vacuum, and that in fact the particle on the inside is the particle on the outside in this sense. And it's very subtle and it's not all calculated, but one way to think about it would be to say, well, you know, the very space-time is kind of stitched together by these quantum wormholes, and these entangled wormholes are like threads in fabric, and only when you have a lot of them do you actually coherently weave them into the fabric of space-time.
Welcome, one and all, to the Cool Worlds podcast with me, your host, as always, Professor David Kipping. Hey, it has been a minute since our last episode. I want to apologize for that, but we took a little break over the summer to recharge our batteries and line up some more great guests for you over the fall semester. And so we've got many awesome speakers coming on. You really don't want to miss them. Over the summer, I had a nice break, I guess, from the podcast, but of course we were so busy with the main channel videos. Over the summer, I think academics, it's not, you know, people think we just take a holiday, like we just go to the beach and chill out or something. And it's really not like that. We do take a little bit of a break, don't get me wrong. I think I took a 2-week vacation in total over the entire summer. But mostly there's a chance to sort of intellectually catch up. I mean, during semester, it is like a bulldozer and running on a rat race almost to try and keep up with everything. There is just this flood of emails and classes you have to teach, you know, service work we have to do, and of course all the extra stuff I do with Cool Worlds as well. So it is a very, very busy time. The summer is a chance where things slow down a little bit, and so I always love the summers because it gives me a chance to catch up on my research, get ahead on some things, plan out for the future, and it's going to be an exciting year. If you don't know, we have JWST, the James Webb Space Telescope, observations coming up this month. So we're just into October. I think it's October 26th that observations are centered upon. And we're going to be observing Kepler 167e, which is really the most Jupiter-like exoplanet, which is transiting its star, you could possibly wish for. We think this planet is so close to Jupiter that it really should have the same kind of moon system as Jupiter has. It might even have a ring system like Saturn. And so these observations are exciting because they are for the first time sensitive to the kind of moons that we know for sure exist in the solar system. So this will be our first chance to see, is this common? Is this rare? And hopefully get some surprises along the way. That's the fun part of science. So definitely look out for that. I'm sure we'll be posting updates on the main channel about that, and maybe we'll do something on the podcast as well down the road about this as the analysis progresses. It will not be overnight, even though we get the data October 26th. It will be a little while before we do the analysis. We'll be doing the analysis as fast as we can, trust me, but it's not like an overnight thing. I'm sure you guys get that. It takes a little while to make sure that we get the signal we want and make sure it's correct and do all of our checks. So please be patient, but trust me, I'm as excited as anybody to see the results of that. But that's exoplanets. So let's maybe today not talk about exoplanets, even though I love talking about exoplanets, and talk about something which is also equally fascinating, perhaps to many of you even more fascinating, and that is black holes. My guest today is really an absolute expert on the topic of black holes, especially thinking about the theoretical aspects of them. The mathematics and how do these things really work. So this is Professor Janna Levin. She's a professor actually here at Columbia. She's a professor at Barnard College, which is part of Columbia University. And she's been a Guggenheim Fellow, and she's also written 4 popular science books. So these are all fantastic titles. I just have to read them out to you because they're kind of poetic. So we have The Black Hole Survival Guide. We all need to know that. The Black Hole Blues and Other Songs from Outer Space. Love that title. A Madman Dreams of Turing Machines, and How the Universe Got Its Spots. And I've read some of these and they're just really, she's a wonderful writer. You want to check out some of these books. They're absolutely brilliant. And if you love black holes, you're going to be very, very happy with this content. So we're going to be talking all about black holes today because this is really the bread and butter that Janna works on. We get into all of it. We get into black holes, the microphysics of them, Hawking radiation, entropy, the holographic principle. Then we get into white holes, wormholes, all of the different weird permutations that people have thought of to do a black hole. So it's a really fun conversation. I think you're going to enjoy it. And please, I'm going to take it away here and I'll catch up with you at the back end of this episode. Janna, the first question I want to ask you, just to get everybody on the same page, is what exactly is a black hole?
So I like to say, just to be provocative sometimes, that I shouldn't think of a black hole as a thing. I should really think of a black hole as a place. And it's a place where there is the creation of an event horizon, which literally is just a region in space beyond which light cannot escape. There are other event horizons that we can think of, but for a black hole specifically, we're accustomed to imagining that there might once have been a very heavy star, and the star collapsed, and in the collapse, it created this incredibly dense state of matter, and that curved space-time so much that it created an event horizon, this region beyond which not even light could escape. The problem with that description is that it's only one way to make a black hole. It's a good description for this one way to make a black hole, which is amazing that nature thought of even that way. But it's not synonymous with the black hole, because when you go up to the event horizon, the matter's not there. It really is just an empty region of space-time. It should be a vacuum. And so a black hole is really kind of a place. It's the place where this archaeological record of this event horizon is imprinted.
It's almost counterintuitive to the normal description then. We normally really do think of this as in terms of the singularity or in terms of this massive object that's right in the center. But your definition there really focuses on the event horizon itself.
Yeah,
right?
absolutely. The singularity is not at all required for the event horizon. Now, in general relativity, after the collapse of this star, this one particular way of making a black hole, the star itself can no more sit there than it can race outward at the speed of light. So that material that formed the black hole is forced to continue to fall, and it leaves behind this empty region and creates eventually, according to relativity, a singularity. It just gets smaller and denser and catastrophically so. And now almost everybody suspects that the singularity will be resolved when we understand the quantum mechanics of that interior nature of the black hole. Even Roger Penrose, in his Nobel Prize winning paper, where he proves that black holes are somewhat inevitable, and he talks about the formation of this event horizon, and he says, well, there's a singularity here, but that's probably just because we don't know enough about physics there.
Yeah, you often hear people just say that a singularity is not necessarily something physical, but it's really a breakdown of theories. And we shouldn't, as tempting as it is, and people get very upset with it. You know, people, you speak to lay people about black holes, and it aggravates them. They're like, well, you can't have, the infinite density annoys us. And we're like, well, it annoys physicists too, right? We're also not happy with that picture. So should we treat the singularity as a placeholder then? As like, we know this isn't quite right. We expect it to be replaced at some point.
Yeah, I like to think of the singularity as, a dying man scrawling in the dirt. It's a message that this isn't going well anymore. Something terrible is happening. And it's a message to us. So I consider it really a signal a helpful signal from general relativity declaring that we are now literally at energy scales where we can no longer ignore quantum mechanics. So it's quite a literal flag saying this theory cannot be trusted without quantum energy scales, which are simply being invoked inevitably by the singularity.
So in this story of the dead star version of how you form a black hole, the mass collapses continuously after the formation of the event horizon, but it's sheathed from us. We cannot see what's really going on.
Yeah, that's right. The event horizon is wonderful one-way mirror. So we're completely shielded from all events, hence event horizon. On the interior, it also means we can know very, very little about what made that black hole. The black hole can't be telling us stuff about what went inside. All I can ever know is the charge, electric charge, the mass of the black hole, and its spin. And outside of those three quantities, I can't know anything about what made it. I can't know if it's donkeys, if it's encyclopedias, if it's pure photons, though they're uncharged. So I guess there's a hint there. But, essentially anything that matches those three parameters, and there's a lot of configurations that match those three parameters, could be inside there. And so it means that there's a lot of information locked behind the event horizon.
Yeah, here be dragons type situation, right?
Yes.
But even though we can't observe it,
Yeah.
if we were to speculate about what was going on inside the event horizon, you mentioned that eventually in this, at least mathematically,
Yeah.
it should form a singularity. And then we're skeptical. Maybe that's exactly what happens.
Yeah.
I guess I have two questions here. One is, how long is that process expected to take? Is it, you said it takes some time.
The formation of the singularity,
Yeah,
or the
in
formation
principle.
of the black hole, or the event horizon?
So after we form the event horizon,
Right. Could
there's
be very
still some mass
fast.
inside that, and it's still collapsing in. Is it
It's
like
actually shockingly fast.
Okay.
For the sun itself is not heavy enough to expire as a black hole. It's not the death state
Right.
the sun is fated for. But if we magicked up a sun-sized black hole,
squeezed it somehow?
yeah, it would be like microseconds.
Wow.
The fall time from the event horizon to the point of the singularity. If you want to make a really big black hole, like a supermassive black hole, and you were to fall in, you could maybe connive to extend your trip maybe up to a year if you were like a trillion solar mass black
Okay.
hole. The bigger the black hole, the slower the
So
descent.
this is all in the rest frame, as if you were sat on the surface of that star?
Oh, no.
So then how does it look?
I have to ask the person falling in.
Okay.
Okay, because so excellent question point to pick apart, and the relativity of time is extremely relevant here.
Yeah, right. Which time are we talking about? Yeah.
Which time are you talking about?
Yeah.
Because black holes deform not just space, but they very strongly deform time. You can think of, as you're outside the black hole and falling in, every step you get closer, you can imagine you're doing a rotation in space-time. So that for somebody who's far away, let's say in a space station that's in a stable orbit around the black hole, it might only be 30 kilometers outside the black hole because they are small. The whole point about black holes is they are small.
Yeah, like city-sized
spatially,
things, yeah.
Right. And so you could be 30 kilometers out and be very safe. Obviously, you can't do that with the sun. You'd be incinerated inside it, So in some sense, black holes are more benign than
Yeah,
stars.
true.
So you could safely orbit this black hole, and according to your clock on your orbit, as your friend, the brave, explorer, falls towards the event horizon, it's as though you see their space rotated into their time and their time into their space. So from your clock's measurement, their time appears to slow down. And it gets slower and slower until, in principle, it grinds to a complete halt at the event horizon. So it's as though they've rotated their time totally out. And their time is no longer ticking relative to your time. It's almost like rotating left 100% into right, So that's the end of it from your perspective. Now, people often ask this, does that mean that the astronaut falling in is going to be hovering outside the event horizon for eternity?
Right, because they seem to slow down
Right.
ever slower. And they, from your perspective, you never actually witness them cross the event horizon.
Right.
Yeah.
But the way that you actually will witness them cross is by acknowledging that astronaut has a little bit of mass and a little bit of energy. And so they themselves back react. They cause a tiny, tiny curvature in the space-time. So you no longer have a pure event horizon, black hole event horizon. You actually have a little bubble that will form, and the event horizon will swallow that person in a finite time. It's a difficult calculation. I don't remember the numbers, but it depends on the mass and energy of the infalling particle. So in a finite time, you will actually acknowledge,
Yeah, but
they
that seems
bubbled
important
in.
because otherwise they
It
can't
is
accrete.
important. They can't accrete, and
yeah.
also two black holes merge in very short order, and they
Right.
would never merge if we saw their times going to zero. And they actually deform away from a perfect black hole solution. You can watch in the numerical simulations the event horizons bubble around each other. They're no longer these perfect, pristine geometries, and then they ring away all the imperfections in gravitational waves, and they settle down to one bigger black hole and go quiet, and that happens fast. Very,
Yeah.
very fast. That's two big black holes, so it happens faster. It's not a tiny thing on a large black hole. And so, maybe your lifespan on the space station has already come and gone. Civilizations have passed on Earth. There's, a new alien in town, and all of that's happened before this astronaut. And from your perspective, falls across. But the intriguing thing is, from the perspective of the astronaut, it just takes a second. And in the same spirit that their time is running so slowly relative to the safe passenger on the space station clock is running very quickly.
Yeah.
And so these eons, millennia, larger measures of time are passing. The astronaut that falls in is like, woo, that just happened fast.
If you think about the kind of this sci-fi story then of an astronaut falling in, like Matthew McConaughey, right? He falls into the Interstellar.
Yeah.
We'll get into that at some point in Interstellar stuff.
Yeah.
But if you witness the universe speed up in terms of its evolution, of course, one aspect of black holes is, they don't live forever. They do radiate away energy, Hawking radiation.
Yeah.
And over very, very long time scales, they would evaporate.
Yeah.
It just makes you wonder, as you fall towards this singularity, would you reach the singularity before the black hole evaporates?
Yeah.
Or would it take infinite time, essentially, and you would leave before that point?
This is all very, very tricky stuff. Well, first, for one, to say that just because it's sort of intriguing, something that you're alluding to is that when you fall in, the black hole can be bright on the inside, because all of this is happening outside the black hole, and the light can catch up to you, fall in behind you. So they're a one-way mirror. They allow light in. So black holes are bright on the inside if there's light raining down, even if they're strictly dark on the outside. And the question is what happens to all of it? Anything that accretes, the astronaut, the light that fell in, the signals from Earth about what happens with the climate, all that stuff. The singularity is an enemy of information. If they truly hit the singularity, it means that in very short order, their quantum information and the information about the arrangement of those quantum bits is lost forever. It's fallen out of space-time. It is an absurd conclusion. It means that it's all gone. So,
which violates many principles of quantum mechanics, right? These ideas of reversibility, that this would be an irreversible process.
Absolutely structured to be, we say unitary technically, but to be time reversible, that you can predict the past from the future, and you can also, I actually meant to say predict the future from the past, and you can reconstruct the past from the future. So that's crucial to the entire paradigm. It means quantum mechanics is wrong, not just like, something else takes hold. It really means it can't be this theory that we've written down that's
or the singularity is wrong? Like, why does it have to be quantum mechanics?
Or it's the singularity that's wrong, exactly. So gravity has to give the predictions of general relativity, or quantum mechanics has to be restructured to contain something really horrible. And if you're a purist, why would you reconstruct this beautiful paradigm that is the most well-tested paradigm in the history of all of physics to accommodate something absurd that's sort of an anathema to what we hold dear as people who like to do physics or believe in the sanctity of physics. So I do think that anyone working seriously on the information problem, which is, as you said, when the black hole evaporates through the Hawking process, eventually the event horizon's yanked up, it's gone, and where'd all the information go, and what was all of that stuff in the radiation? That crisis, it will really, most people today would really advocate that it's general relativity that's going to have to give, and that quantum mechanics is going to reign. And the resolution will mean there are no singularities that take information out of the universe. Something very different is going on. And intriguingly, the difference might not be at the singularity. It might happen way further out at the macroscopic event horizon. And I think that realization over the past few decades, really since Hawking, inspired this crisis, I really think that more and more people are going to this idea, quite surprisingly, that it's not at the interior of the singularity that this is going to be smoothed out. It's going to be at the event horizon.
So let's just, I do want to talk about the information paradox. Let's just slow it down a little bit.
Yeah, because that's a lot.
Yeah. So first, the problem.
Yeah.
So if I have a book with an encyclopedia or something, and it's got lots of information, and I throw it into the black hole, that information is seemingly lost to the universe.
Yeah.
However, we think eventually that information, should get back out by this reversibility principle. And we do see radiation come out of the black hole, or at least we haven't actually witnessed it, but we think it should happen, which is Hawking radiation. And so the temptation is to say, well, maybe the Hawking radiation somehow encodes that information and carries it away.
Seems sensible.
But this is really your expertise, not mine. But my understanding is the Hawking radiation are, almost like pair particles formed in the event horizon, which are entangled with one another. And so how could they be entangled with one another, but also entangled with that encyclopedia I threw into the black hole 2 years ago?
Right.
Like, how does that information... It seems like entanglement is strictly monogamous, and this wants to open everything up.
Yes.
So maybe I'm misunderstanding some parts of the problem, but that's my understanding.
That is the problem. So let me try to slow down even more about what Hawking showed in the very beginning.
Okay.
And he didn't show it this way. He used semi-classical quantum mechanics on a curved space-time and looking at modes and really beautiful language about in-states and out-states. But there's a simpler way to do it in hindsight, which is just to imagine from empty space, and this has, in some sense, nothing to do with the black hole. In empty space, it could be happening in the empty, flat space where there's no stars, no matter, nothing. According to the Heisenberg uncertainty principle, I cannot know exactly the location of a particle or exactly its energy, let's say momentum, at the same time. And that uncertainty is profound. It's not one of a fogginess of the ability to measure. It's actually saying, a particle doesn't assume a definitive location state, eigenstate, we would say, simultaneously with assuming a momentum state. And one analogy I like to give is it's like chords in music. You can play a single note, or you can play chords, which is a composite of notes. In some sense, a chord, a momentum state, is a composite of position states, notes. And you can do one or the other, but you can't do both simultaneously. And so, this was very profound in initiating quantum mechanics, but in this context, it suggests that I also can't say a particle's not there. I can't say a particle's exactly here. I also can't say it's not here definitively.
Yeah.
And so there's a sense in which empty space by the Heisenberg uncertainty principle allows you to make particles as long as they go away really quickly. And they have real energy. It's just a fluctuation. But the problem is they have to have they have to come in pairs because they have to cancel out any of their details in order to have come from the vacuum, which has no information in it in some sense. It has no charge. It has no So if I make an electron, let's say, I have to also make a positron to get rid of the charge for it to have come from a chargeless vacuum state. Okay, so now I have this entangled pair, and now I know I have them anywhere in space. They're happening, they're bubbling, frothing. The black hole does this really sneaky, naughty thing. It has this big event horizon, and it takes one of them. It takes one of these particles. And essentially, because of the event horizon, it separates this entangled pair. And now suddenly, if it's, let's say, the entry particle that's hovering outside the event horizon, it doesn't have its pair to join to reproduce the conditions of the vacuum. It can't go back into the vacuum. It's now a charged particle without its annihilating pair, and it's stuck. And so it will escape. It's got nowhere to go. So it'll just radiate out to infinity. And the reason why the details of this story are interesting, the reason is because it suggests that that particle had nothing to do with the black hole or anything that ever fell into it. Nothing at all.
Yeah.
And so it can't possibly carry the information out. That was Hawking's original suggestion.
This happens way away from the stuff that's deep down.
Yeah, it has nothing to do with the stuff that's deep down.
Yeah.
Now, you were making this interesting point. Well, maybe there's this subtle way to entangle the particle that fell in. Somehow with the radiation that comes out, the particle that fell in a long time ago, not the pair. So now I'm trying to non-monogamously entangle the thing that escaped with its pair that fell in, and then with something that fell in, a billion years ago. Yeah. And that is not allowed by quantum mechanics, and it's very tricky. So the story was never easily resolved. It's a really hard problem. So now you're kind of stymied. Well, I don't know how to solve this problem because for the information about what fell in very, very long time ago to make it out, you would want to leverage this property of entanglement, that the information could come out if it was quantum mechanically entangled with the stuff that radiates. That would be a viable mechanism given by quantum mechanics to get information out.
Can I just ask, was Hawking aware of this problem when he wrote his, was it 1970s, the seminal Hawking radiation paper?
Yeah.
Did he immediately realize this, or was this something that others pointed out?
I think he did.
Okay.
And if you ask people like Lenny Susskind, who says he was totally pissed off about the whole thing, people like Lenny were faster to realize than other people on the quantum side what a big deal this was. I don't think it was immediately obvious to the community, but it was to people like Tufte, Nobel Prize winner, and to Lenny Susskind, that this was really a big deal and this was a really big problem. And if you listen to Lenny's description of it, Stephen was kind of, taunting.
But it seems like surely it's surprising in a way it makes things worse for them, because it offers some hope of getting something out of the black hole.
Yeah.
Whereas if you don't have Hawking radiation, nothing ever gets out. How is that more palatable than...
Because the information, as long as it is, as long as there's a kind of protection conjecture that we on the outside will be protected from this violation of the laws of physics, many people were willing to overlook it. Okay. And it is a good question. Wouldn't a purist be offended that even if the event horizon lived forever and there was no Hawking radiation, that the information's leaking out of a hole in the universe? And actually there's this kind of, well, if I can't see it, it doesn't really exist.
It's intact, but we don't need to worry about it because we can't see it. It's just, the information is still there, but just we can never open it up.
Maybe the information fell out of a singularity, even worse. Yeah. Maybe it did, but I don't really care because the rest of the world is protected from these violations. So these violations of the sanctity of quantum mechanics and physics are simply, by the laws of physics themselves, isolated and away from us and can't harm us and can't harm the universe. And so in some sense, it's silly to argue about whether or not it exists.
We'll be right back after this message. Hey, I hope you're enjoying this episode about the information paradox concerning whether black holes can destroy information or not. Information is pretty important, not only in physics, but of course also in our lives. And it is not just black holes that try to hide information from us. Sometimes the news and media outlets we rely on also conceal important facts from us in order to align with some political ideology or narrative. And that's where today's sponsor, Ground News, can help. It is a website and app designed by a former NASA engineer who wanted a more objective look at current events. It gathers news from a diverse range of sources, and it lets you see the political bias, credibility, and ownership of each story. So, for example, concerning the recent news of the first launch of a new Chinese megaconstellation, you can quickly see the different ways in which it is being reported, and a handy chart pops up revealing that of the 49 sources covering this story, only 7% are right-wing. And that's interesting. It means that if I only read right-wing media, this would be a blind spot for me. To address that, Ground News have a blind spot feature. There's a tab on the app and the website called Blind Spot that shows you the stories that are being missed by both political sides. So, for example, if I only read left-wing articles, I'd probably miss the news that Elon Musk has accused FEMA of blocking SpaceX relief efforts in North Carolina. I think that Ground News has become an essential tool for getting an objective view of the news landscape today, encouraging readers to explore their curiosity. To get started, head to ground.news/CWP, as in Cool Words Podcast. That'll save you 40% on the same Vantage plan I use for unlimited access to all of their features. Once again, that is ground.news/CWP. Now, back to black holes. So you mentioned there are these more macroscopic solutions. I've heard things like the firewall, the holographic principle being invoked to try and explain this.
Yeah.
There seems like there are several ideas, maybe many ideas out there proposed to solve this paradox. Has the community at this point, because this is not a young problem, right? It's been around for decades at this point already.
50 years.
Yeah, so it's been around a long time. Has the community come to a quasi-consensus around one solution? And what
I
is
wouldn't say exactly, but it definitely feels like there's momentum in a certain direction. And let me also say that the problem is a profound one. And so it means that it's telling us the reason why it's not just this niche problem, what should we really care about it, is, black holes take longer than the age of our galaxy by a lot, to evaporate. We're never going to have to confront this problem. Why are so many people interested in it? And the reason is that it is the terrain on which we are understanding quantum gravity. It is giving us all the clues. It's the only surface. So that's why not just astronomers and astrophysicists think about black holes, but pure theoretical physicists who are interested in string theory think about black holes, because it is the terrain on which we are getting all of these clues. Hawking's observation was a clue that the black hole's telling us something about quantum mechanics and gravity and how those two are going to come together. And the information loss problem, by being so difficult, has been so helpful because it's pushing us up the hill.
So it's a gift. It's like the universe has given us this gift of challenging these two theories.
It's telling us, not that direction, that doesn't work. This way, nope, that avenue is closed off. It's like a maze, okay? And if we keep trying this maze, it will guide us to the one path outside of this maze by closing off all the others.
So where are people at? What's the leading contender?
It's really interesting. I think it's really just the most exciting turn, and it's come slowly and fast at the same time. I think the ideas were already back there in Hawking's original work, and people like Ted Jacobson and Penrose and Unruh. The suggestion is that maybe it's only quantum mechanics. So let me kind of go with the far, and then we'll peel back and kind of pick apart how we got there. I think the direction things are going now is to suggest that maybe gravity is not a part of the fundamental description. When we talk about the laws of physics, we talk about matter forces, the electromagnetic force, which is now merged as the electroweak force, and the strong force, which could pretty comfortably be merged in some grand unified theory if we understand some things, pieces. So it's really just matter on one side and quantum mechanics, and then gravity, this outlier on which all of this plays out, this big space-time. And I think more and more people are starting to think, space-time only emerges out of pure quantum phenomena. Things like entanglement actually create space-time. So I can think of there's a saying that's been going around due to Juan Maldacena and Lenny Susskind, which is ER equals EPR. ER is an Einstein-Rosen bridge. Einstein and his collaborator Rosen discussed wormholes, essentially, which are pure space-time phenomena connecting one point and another point. And in the same year, 1935, they wrote another paper, EPR, Einstein, Podolsky, Rosen. Right? Mm-hmm. Am I right? Sounded weird for a second. And there they talk about quantum entanglement. They were the ones that described, I have, a pair of particles, and it's like a wishbone. I break it apart and I take them to different regions of space-time, and I look at one piece and I see, do I have the small piece or the big piece? But unlike the wishbone, they're simultaneously both small, big, big, small. And they haven't collapsed to their different states until I disturb this very delicate entanglement. And they didn't connect them. But this epiphany was, maybe entanglement is related to Einstein-Rosen bridges. So you describe the Hawking particle that escapes, entangled with its pair that falls in. How can it also be entangled with some information? Well, it can if there's an Einstein-Rosen bridge connecting them. If the particle on the inside is the particle on the outside, and it's not a different particle, then I can preserve the monogamy of entanglement, and I can get the information out. So the idea is like there's little wormholes that are stitched across the space-time.
So let's just ask a question about this. So if we were to throw a particle in, like a little buck, we threw that into the black hole. Yeah. It somehow spawns an antiparticle to itself. when it crossed the event horizon, and that's what radiates.
Well, no, I think the argument would be that when it's broken up into its quantum bits, that there is the possibility, and nobody's calculated this, and let me not overstate it. We'll get to what people have calculated, but there's an intuition that there could be a wormhole connecting that particle with the particle that is in the radiation that is escaping from the vacuum, and that in fact the particle on the inside is the particle on the outside in this sense. And it's very subtle and it's not all calculated, but one way to think about it would be to say, well, you know, the very space-time is kind of stitched together by these quantum wormholes, and these entangled wormholes are like threads in fabric, and only when you have a lot of them do you actually coherently weave them into the fabric of space-time, in which there's a description of an event horizon. And so maybe space-time itself is simply a fabric that's emerging from these quantum threads. That is kind of a more metaphorical way of describing it.
So this requires, I mean, obviously it requires entanglement, and no one's...
Yes, it's pure quantum mechanics in a sense. And the gravity, all the space-time stuff we're used to talking about, metrics and measures of curved geometries, aren't good descriptions when I look really closely. And we have examples of this all the time. The temperature in this room is a pretty good way to talk about the huge numbers of atoms moving at their particular energy. Pretty good average to talk about the temperature. I definitely feel it. I'm not thinking about gazillions of atoms, right? But if I look really closely and I hone in smaller and smaller, there's no notion of temperature. There's no particle that carries a quantum number called temperature. It simply only emerges in the vast collective behavior in these equilibrium systems. So it might be similar at spacetime. I get down to a certain level, there's no clear notion of a smooth spacetime.
I think I can accept the idea of entanglement this way, but the wormhole seems like I don't know if you're using that as an analogy to make it easy to understand, or if you really do mean there are actual wormholes between, because I think
people are saying there's an actual bridge that can transport the particles outside. But one way to talk about this, I think, maybe is to go back to holography. And like maybe that's a useful, so what was actually done? Why are people talking this way? Even intuitively, where's this intuition coming from? Why are they trying to make this connection? The story of holography is the idea that all of the information interior to the black hole, the whole volume of the black hole, however much that is, can never exceed the amount of information that you can pack on the area of a black hole. And this goes back to
on the surface area,
on the surface area, that event horizon. It's this exactly inscribed proportional to the event horizon. And there are laws of black hole thermodynamics that emerged from all of these studies, back in the 70s, that really had this thermal character. Talks about entropies and temperatures, and all of those things have to do with the area of the horizon and nothing to do with the volume. So let's say I have an area in this room and I try to pack some information on it, and it exceeds the information that I can pack on the area of any region of spacetime, not even a black hole. I will make a black hole. And so the black hole is telling us there is a fundamental limit in nature to how much information you can pack in any volume. And it is limited, surprisingly, by the much smaller dimensional area. Now, this is holography in the sense that a hologram is completely two-dimensional. It inscribed to all the information's only in 2 dimensions, and it's simply an illusion that we can make it look like a full 3-dimensional object. And the idea of holography is that this is true about the world, that we are all holograms, that it's an illusion that we're projected into this higher number of dimensions. Now, that was a suggestion hinted at by the math of understanding Hawking radiation. But then Juan Maldacena comes along, and it's the most highly cited paper in the history of theoretical physics. Okay. He writes a paper. I looked at the title recently because I was talking to Brian Greene, and I'm going to try to remember the title. The Large N Limit of Supersymmetric D equals 10 Gauge Theory and Supergravity. I think that's his title. Or maybe it was Superconformal Theories. Anyway, what Juan showed was that if he looked at a volume that had, as laws of physics, field theories, quantum field theories, and gravity, that he could prove that it was completely analogous, more than analogous, that there was a strict dictionary between that description and a description on the boundary. Imagine a sphere for the sake of argument. So you have a universe inside a ball, and on the surface of this sphere is pure quantum field theories. No gravity is even in this description on the boundary, and it's lower dimensional. And he proved that those are absolutely equivalent descriptions of this particular universe. Now, what does that mean? It means I don't need gravity to describe the universe. I only need quantum field theory. And it means I don't need the same dimensionality as I think I live in. I need one dimension less to describe the universe. So it's a precise example of holography. It says the laws of physics on the boundary completely encode this world that has gravity and black holes that evaporate, and do they lose information or not, and oh my God, and all this stuff. It is completely the same as a universe on the boundary that has no black holes, no space-time, no gravity.
So wild.
It's stunning.
Yeah.
It's stunning because it says, well, then therefore no information can be lost. I might not be able to write the script for exactly how it happens yet, but it means that if that's true, the information can't be lost because my theory on the boundary does not lose information, period, and they're the same. So even if I can't figure out how it happens with the black hole specifically exactly, it can't happen. And so that when that happened, that's when people like Hawking started to say, okay, I yield. I concede. Information is not lost. And even though there still wasn't the kind of proof that you and I might like to see, or accustomed to seeing.
So we've mentioned wormholes. I want to ask about it one more time, because wormholes is always one of those things that is just fascinating, because it's played around in science fiction so much. And if, wormholes are truly real, as you're kind of invoking them to explain the information paradox. One unpalatable thing about them is they allow for these grandfather paradoxes and causality violations, right? So you could have, I could birth a wormhole with two mouths, and I could accelerate one away in a spaceship at high speed, and then close to the speed of light, and so that would cause a huge time dilation. Or you could put it near a black hole or something, create huge time dilation, bring them back together, and now they're displaced in time. And so you could jump through and do these grandfather situations. So I know that Hawking was always really averse to that, and he had his chronology protection conjecture, right, to say that this, whenever you try to invoke anything that allows for time travel, the universe will just somehow have a rule that won't allow you to do it. And so if we allow for a universe that permits wormholes in this context, doesn't that open the door to, maybe it's just in a microscopic scale and then we don't have this problem, but doesn't it open the door to causality violations and these other problems?
Not necessarily. There are ways to burden the wormholes where it's not so easy for them to do those things. It is part of like a chronology protection conjecture. But it's kind of, how do I say this? Is it so bad if a quantum particle can go back in time? It's already doing bad things in the state of entanglement. It's already violating the information traveling faster than the speed of light in some sense. Some sense.
That seems a controversial statement, though.
It is a controversial statement. Like if me and my friend are one's in Andromeda and I'm here on Earth, and we're looking at our entangled particles in the wishbone state, trying to see which one of us have the big piece in the quantum entangled system. We can't relay that information to each other faster than the speed of light. So if I look and I see I have the big piece, I don't know that I'm the one that collapsed this delicately entangled system, or if my friend in Andromeda collapsed it. And to figure that out, I'd have to send a message less than or equal to the speed of light.
Right, so you can't communicate faster than the speed of light.
Right, there's no classical information that can be propagated faster than the speed of light. So it's very strict. That quantum information seems to be, in some sense, tossed around a little more freely. But no classical information can be tossed around so freely.
So is there a way then in a larger, how would you take a black hole or two black holes? And we might imagine they have these in space-time, these kind of these holes that plunge through this grid of space-time. And in a wormhole, we kind of imagine those holes being connected and providing a tunnel. Is that a reasonable description? How do theorists think of a wormhole potentially forming?
Well, they're not necessarily thinking of such large macroscopic wormholes that are simply connecting what would have been a singularity. Imagine literally like on fabric, cutting it out and sewing in a nice wormhole. It's not necessarily that large scale, literally quantum level. And so the wormholes are from particle to particle, and they're threading across the event horizon. And again, I'm hand waving because so is everyone else.
Yeah.
I'm not trying to put this on the same level as Maldaceno's dictionary between gravity and a quantum field theory. That's very precise and very heavily worked out. This other is still, it's an idea.
So you're saying microscopic quantum fluctuation type wormholes, that's fine.
And those are like little threads, and then the threads sewn together create this impression of the event horizon that's evaporating, and that whole description emerges solely out of, if I look at it very closely, it's like, oh, it's really just these threads.
Okay.
That's really all that's there.
I guess that has no bearing necessarily on the reality or plausibility of the sci-fi macroscopic
I think
wormhole.
the sci-fi I'm just saying that the sci-fi conversation, which is fascinating, requires a larger coherence of a coherence. We're talking about a more macroscopic scale. And could you build a macroscopic wormhole big enough to put a clock in it and send it back, or a person to go kill their grandfather before they had progeny? That is it is different. It's like saying, it is back to like the temperature of this room. Some things emerge only out of the collective of large numbers of things. And then there is a transition between the kind of phenomena that you can experience at that large scale. I can't yet experience quantum entanglement. It's not that different than the Schrodinger's cat, kerfuffle, which is to say it's just very hard to keep things entangled on large scales. It's just very hard. And so similarly, I think some of the problem or some of the things that we might find are unhappy in quantum entanglement or contrary to our experience or hard to accept aren't part of the conversation when we get to macroscopic scales. And we talk about large wormholes over large ranges in physical universes connecting our solar system to another. That wormhole doesn't have to show chronology violations, even if we do see it on the quantum scale.
Another, I don't know if it's connected to the wormhole idea really, but it kind of reminds me of it a little bit, is with a spinning black hole, with a Kerr black hole. I guess we already talked a little about the unphysicality of the singularity, but with a Kerr black hole, my understanding is the singularity isn't a point. It would spread out into a ring. And it kind of raises the interesting question I've always wanted to ask someone like you, Janna, is what would happen if you were falling towards this ring? Would you be able to, in principle, pass through the center unharmed, unobliterated? And if so, what would be your fate after that point?
Well, it's even if it's a great question, and the ring makes it look like, oh, maybe there's something in the spinning black hole. But in some sense, I could ask the same question about the singularity in a non-spinning black hole, which is just a point. I could say, can't I avoid it? I mean, it's just a point in the center of a sphere. Just don't go there. Hang out, put yourself in orbit. And orbits are free fall. I don't require engines. Once I'm on my orbit, I can just fall there for eternity, the way the Earth does around the sun. Just don't go there, And the problem is, because of this rotation of space-time conversation, is that once the observer enters the event horizon, what you on the outside thought was the center of a spatial sphere, a point in space, to the person falling in, because this complete rotation of space-time has happened, they measure that as a point in time. So that point cannot be avoided any more than a future instant can be avoided. You can't jump around it in time.
You're going to hit it.
It is inevitable. And you can draw a space-time diagram where you convince yourself, oh man, that singularity is in their future. It is not in their space. If it was in their space, they could avoid it. Just
So
like you can
you would
avoid
hit-
the event horizon.
So
Just
you'd
stay
hit
away
the
from
ring
it.
then? Is this what you?
So similarly with the ring,
Yeah.
it cuts across their time, and there is no timeline that allows you to avoid the ring. So while we on the outside like to describe it as a spatial ring, and we like to talk about the center of the non-spinning black hole as a point and the center of a sphere, to the person falling in, these are points in time.
Yeah, you've destroyed one of my sci-fi dreams. So we're always trying to look for those ways out. There's a couple of topics I want to make sure we have time to talk about, because I asked folks who are supporting the Cool Worlds channel things to ask you, and they had lots of great ideas.
Oh, nice, fun.
And before primordial black holes, I want to talk about. Before we get there, maybe we'll just finish with white holes, because I feel like this kind of connects to our previous discussion.
Yeah.
So my understanding of a white hole is that it's a solution to Einstein's field equations, but it's essentially just a time reversal of a black hole. That's really all it is. And so it's almost like a mathematical
Think
construct.
of it as a Big Bang. Singularities in the
Yes,
past.
right.
Energy comes flying out.
So it spits
it's like a
stuff
Big
out.
Bang.
Now, when I hear that description, it often kind of ends there. And I guess a natural question is, well, how would you make such a thing?
Yeah.
Obviously, maybe the Big Bang, people do often write out. I've read several
We do
articles
believe
recently
in how to make it.
comparing
Yeah.
the black hole, the white hole to the
Yeah.
Big Bang, and people arguing forcefully that we should not make that comparison. The Big Bang is very, very different from a white hole. But is there a context in which we can imagine a white hole forming? What would be the formation scenario?
So I've always loved this stuff. I think that there's two ways we can think about it. The early days, people were just like, hey, do these pieces of space-time sew together? So that's less causal. They couldn't say, oh, this happens and that causes the interior to become a white hole. So it's not predictive in the way that we like. Matter does this and then that causes the Big Bang or something like that. It's more like, hey, do these two pieces of fabric, can I sew them together smoothly? Does it make a continuous, smooth space-time? I can't just sew some crazy orbifold onto it. It's like a quilt. Can I sew these two pieces together smoothly? And you can. So that's kind of the first observation. And it's pretty appealing. Where does the stuff go? It goes into a new universe, The problem is, the reason why some people object to this so much is because each time I throw something in, I have to create a new universe.
So what do you mean if it's a white hole, you can't throw something
If
into
I
it?
throw something into the black hole,
Okay.
and it
that
approaches
connects
what
to a white
would
hole.
have been the singularity, and it instead escapes into this white hole.
Okay.
So the black hole, no matter how small it is on the outside, we talk about how small they are, city-sized, they can be very big on the inside. It's like, I like to call it Doctor Who's TARDIS, and so you could have a whole universe in there, which is pretty stunning. So the particle falls in, it goes into a new universe. Amazing. That way information isn't destroyed, it's simply gone somewhere else. And it's highly unstable to people who think about entropy and adding up what is the most likely thing to happen in the universe. We tend towards these higher entropy states. It just seems catastrophically unstable to imagine that, let's say a little electron falls into the black hole, that it creates a whole universe. It has this power to do that. That just seems very entropically high and therefore very entropically unstable. Why wouldn't that start happening everywhere? Why would it be limited to there? People have worked with these things, but I think more than anything, the issue of the information loss has just steered people away as to whether or not that is the most intriguing place for us to be having our conversations, because that conversation has spiraled so far afield, so far away from the singularity. And it's all around the event horizon now that people have lost some momentum, of group, community effort and interest. But
plus we know that black holes are out there.
Yes.
We've never seen a white hole. So it would
Right.
be odd if we live in a universe where
Yeah.
this is allowed, but there are no examples. If
Well, I
everyone
think-
has a partner, why don't we have any? We should have equal numbers of white hole partners, right?
Well, that's curious. They might just literally be other universes and never popped back into the one from which the black hole originated. So maybe you can hide that, but that's not that different in intuition. It's a correct intuition in the sense that that's kind of the entropy arguments. Well, why wouldn't this be happening all the time in some sense? If it's so easy to do or it's so likely. But you could say, well, the Big Bang is a pretty intriguing example, even if technically I try to disambiguate white holes, strictly speaking, from Big Bangs. They share a lot in common. And maybe the Big Bang, maybe that somehow we can't think that it's the only one anymore. We don't talk like that. We don't talk like our universe is the only one or the Big Bang is the only one. It's just the only one we have access to.
Yeah, just like looking for intelligent life in the universe. We're the only ones we have access to right now.
Right.
Hopefully one day we'll have more. So let's talk about primordial black holes, because people were burning the bit to talk about this. And the primordial black hole is interesting as a black hole that forms not from the conventional way of a star dying and collapsing and falling, imploding into this tiny object.
Yeah.
Primordial black hole forms near the very beginnings of the universe itself, and it has been suggested as serving some utility as a potential dark matter candidate. So maybe we'll just start with your description. Like, how do these things form spontaneously?
Yes, I actually think that they're very profound prediction or maybe hypothesis. I think that black holes are unlike any other phenomenon in the universe that's macroscopic. They are much more like microscopic, fundamental particles than they are like macroscopic stars. And that's very profound, I think. So if I think of what is an electron, an electron isn't like a little bit, mine's a little heavier, or this one's a little lighter, spins a little faster. That's not an electron. An electron is exactly this mass, exactly this spin, has exactly these quantum numbers. That is what it means to be an electron. There aren't electrons that have those quantum numbers and also have other qualities. Okay, that is it. That's the entire story. There's something fundamental about particles that show that characteristic. And we think that even if I go to string theory and I look deeper, I say, oh, it's not really a fundamental particle, the electron. It's a vibration on a fundamental loop of string. That is still what it means to be an electron, that set of quantum numbers. Okay. Black holes seem to have something like that in the sense that we started.
With just these three numbers.
These three numbers. They're fundamental. I cannot tell the difference between one black hole and another if they have these three identical numbers. In the same way I can't tell one electron from another. It's not like, oh, that was my electron that I sloughed off earlier today. There's no meaning to that.
But those numbers aren't discretized, unlike...
They're not. They might be at the primordial level.
Right.
Okay, it's a good point. But a ball of electrons starts to not seem discrete anymore. If I have huge numbers of charges, I don't notice that it's discrete. And of course, that was a very surprising discovery, that charge is discrete. It may be the same with black holes. That eventually, if I go to primordial black holes, why are they made in the Big Bang? Because all fundamental particles are made, and black holes are fundamental particles. They're a fundamental particle in the spectrum, the particle spectrum that nature produces.
But just a very massive particle, would they be? Or?
They would be very massive, yes, but still quantum massive. I mean, even if I'm talking about trillions and trillions of times the mass of the electron, it's still tiny.
But if I make them too light, they would Hawking radiate away.
That's right.
Within the age of the universe.
So there's different questions. One is, what are the first black holes made in the universe? The very first. Those are probably Planck mass, 10 to the 19 GeV, which is a unit of billions of electron volts. Some people have heard of electron volts. And that's much, 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 much heavier than the mass of an electron.
Yeah.
So they're incredibly heavy as tiny fundamental particles, but they are still tiny fundamental particles. And all of their quantum numbers would be discretized, presumably. Now, whether or not it can still talk that way at the Planck scale with all of this stuff going on and sewing fabric of spacetime, are they really fundamental? Maybe all that is tossed away. But this is how people got started talking about the primordial black holes, is we expect them to be made in the spectrum of fundamental particles that are made in the Big Bang. Now, those, like you said, the smaller they are, the hotter they are in the Hawking sense, and they would essentially explode. And they would
So
be
the
gone.
Planck mass, they wouldn't be here by now.
Yeah, they would be gone. But, if I can keep making black holes through other processes, because also weirdly, unlike other things, they are made astrophysically. I don't make giant electrons. I might make giant neutrons in neutron stars.
Yeah.
But I can make these giant things that are also fundamental particles. That's why black holes are this exceptional and fascinating and ubiquitous in studying science. So in that case, it's easier to make primordial black holes out of collapse of stuff that has like the density of air in the early universe. And that might be surprising, but you can make like these sort of bigger black holes out of the density of air. And there's a certain sweet spot where the black holes would not have evaporated yet. And they were made not by the death state of stars, but they were made in the early universe, and just not maybe the instant of the Big Bang. And they could, surprisingly, just by doing numerology, account for dark matter. And you wouldn't see them evaporate because the bigger the black hole, the cooler they are, and those would be cool enough to live until today.
If we kind of rewind the clock to their formation, with dark matter, I think there's a lot of evidence that they can't be baryonic, right? Whatever it is can't be baryons. And so just by looking at sort of the cosmological matter density of the universe and lambda CDM models, this seems to be prohibited. So does that mean the primordial black holes in this context would not have formed from matter? They would have formed from the cosmic soup of energy, essentially.
Well, yeah, I mean, the black holes I was describing as these Planck-massed black holes, in what sense are they formed from matter? They're just part of the spectrum of particles that's created. We could have made them at the Large Hadron Collider, conceivably. If they are a fundamental particle in the list of particles, then I can make them the way I make a Higgs particle. They're not made from other kinds of matter in that sense. And so that's why they can be dark and non-baryonic, because they can just be.
And would they merge together in the same way that we see
there's
mergers of
right, you
macroscopic
can
black holes?
hierarchically try to merge them, or you can just say, maybe I don't know how they got there, but let's just do the phenomenology and just let's see if they're a plausible candidate, and then we'll worry harder about how they got there. I mean, after all, I don't know how the supermassive black holes at the center of the galaxy got there, but we continue to observe them and look at them and theorize about them and look at quasars, even though we don't know how they got there.
So I guess it'd be fun if they had charge, because they can't have charge.
Then they're not dark, because all electromagnetic charge interacts with photons. So light will scatter off of any electric charge, as will other charged particles, exchanging photons through the electroweak force or electromagnetic force, and they won't be dark. And so they would no longer be dark matter. They would be luminous. And in fact, we talk about charged astrophysical black holes as a way of looking for black holes, because then you're looking for particles scattering off of the electromagnetic fields around them. It's not that the black hole's emitting light from its interior, but you have particles that now get caught in the electromagnetic fields. And with any charged particle, you have interaction with photons, and it can reflect light.
Well, isn't
and scatter
that
light.
a knock against it then? Because surely you'd expect some fraction of them to have some residual charge.
Well, that's very interesting. So a lot of the arguments, I will play devil's advocate about charge, because I'm very interested on the astrophysical side in charged black holes. So the argument against charge is that, look, gravity is so weak compared to electromagnetism. It's so weak that if the black hole is positively charged, it's not going to equally draw in negative and positive charges. The repulsion of the positive charges is totally going to dominate over gravity, and it's just going to siphon in any negative charge that happens past and neutralize. Okay, so it's very difficult to maintain charge on an object out there. It's actually quite hard because there's all this stuff flying around, and it will want to neutralize. Electric fields want to screen, and they will naturally neutralize. The argument, that argument is probably pretty good in primordial black holes, that sure, they might get charged, but ain't going to last long. And The reason why it's interesting in the astrophysical ones is because black holes in magnetic fields, spinning black holes in magnetic fields, you can prove that the ground state, the low energy state, is to acquire charge. They want to acquire charge in that special circumstance.
But then isn't this where your analogy of them being fundamental particles maybe hits a wall? Because a proton and electron, you could say the same thing. Like, okay, there shouldn't be protons or electrons out there.
And they do. They find each other and they annihilate. That is a problem.
No, a proton and electron.
Oh, okay.
Not a positron. I mean, they form atoms, right? They bind. They form hydrogen.
Which is neutral.
Right, which is neutral. And so therefore, if they really were behaving as elementary particles, would they not then
see your question.
Form a black hole,
right,
in a
like a black
nucleus
atom or something. So I think if we really think, and again, these are being challenged by the current ideas of quantum field theories, conformal quantum field theories being the entire description. But if there is this kind of fundamental gravity description, and if black holes are made primordially, we don't expect them to be charged. We expect them to be in the gravity sector, not in the electromagnetic sector. So the primordial ones, we don't expect them to carry electric charge.
Okay.
But once they're growing and accumulating and getting a hierarchy and they're, getting contaminated, you could ask, well, should I be looking for little charge signals? And so we do expect them to be electrically neutral and really have all the properties of dark matter in that case. Of the primordial ones.
So we could make a black atom maybe in the lab, potentially.
Yeah. I mean, if you really want to push it, a supermassive black hole, I guess we could say, is like a nucleus, and a little black hole, 10 times the mass of the sun, little by comparison to millions or trillions of times the mass of the sun, is like in orbit around it in a Bohr model of an atom. I mean, you could, kind of look at it that way. And they can stably exist like that. And there could be something like 20,000 black holes of stellar size swarming around a single supermassive black hole. It's just that a lot of other junk gets in there too.
So do you consider this a serious candidate for dark matter, or do you sort of lean on the more axion or WIMP type models that most astronomers seem to be leaning towards?
I'm very agnostic about dark matter.
Yeah.
I don't myself feel impelled to pursue it. So somewhere in my gut instinct, I don't think it's the way to go. But I think we have to be agnostic about it. I mean, the world is really strange. And every time, there's not dark energy, that's ridiculous. There's not dark matter, that's ridiculous. Good reason 30 years ago to be like, there's not dark matter. That's insane. That's silly. I mean, I remember my professors, even as late as like 2000 or late 90s being like, that's ridiculous. Okay. So it is, we have surprising results. Black holes evaporate. There is dark matter. There very likely is dark energy or something going on out there. And that means that this incredibly neat package that we have with all the bows tied on it of the standard model of particle physics just is a tiny part of some grander story. Now, you got to be thrilled with that for a theoretical physicist. There's nothing worse than having a complete solution, because then you're like, now what do I do?
Yeah, it's definitely a great time to be a theoretical physicist. I definitely feel that. So let me finish off, because we're running late on time. I would just want to ask you about Pioneer Works and the other things you're doing besides from studying black holes. Tell us about what Pioneer Works is and how people could maybe visit and get involved.
Oh, amazing. Pioneer Works is a real labor of love. It's a cultural center in Red Hook, Brooklyn. It was founded by the artist Dustin Yelland and his cousin, Gabriel Florence, who became the founding artistic director. And then I came in after Hurricane Sandy hit in the very early days when they were trying to piece together this old ironworks factory from the late 1800s. And I was on sabbatical and I was finishing a book on black holes naturally. And I was looking for a space to finish writing. And I always hang out with artists secretly. My whole life has been kind of marching towards this collision with artists and scientists. And we all kind of fell in love. We formed a little triad, and we've been working on Pioneer Works ever since. When was Hurricane Sandy? 2013.
And what do you guys do there? What's the type of events?
It is a cultural center that is We have artist residencies, we have tons of art exhibitions, and we have a lot of conversations with scientists. Sometimes we relate these. For instance, we'll have an exhibition, an art exhibition that makes us think of neuroscience, as we did with this artist, Charles Atlas. And then we will invite neuroscientists in the context of the exhibition. And we'll have 800 people will come. I mean, it's really surprising to us, even the appetite and the interest and the enthuserson.
Are these free events or
These
ticketed,
are
or
we
how does it work?
all my science events are free. All
Okay.
the exhibitions are free. Mostly 80% of our events are free. Occasionally we'll have a music event that's ticketed, but by and large, almost everything is free and open to the public. We very much believe that this is where culture is pivoting. That when we think about art and science and we have access to culture, that we are thinking better in terms of our entire orientation, that these things belong to all of us. I feel very strongly. And as scientists, that's something we know. We know that idea. Data has to be shared, eventually released to the public, that Hubble's images can't be bought, they're free. That we have a strong sense that what we do belongs to the world. And I think that is our really guiding principle. We used to sit around and say, we're building the world we want to live in because it doesn't exist yet. I think there's never been a place like Pioneer Works before that really has art and science as these very strong pillars in this just mission to have culture accessible to all. And
So
our
where
big
can people head to the website or something?
Yeah,
or,
so you can go to pioneerworks.org.
Okay.
We are a nonprofit, and you will see lists of our upcoming events, science exhibitions. We have these open Second Sundays events, the second Sunday of every month, where you can visit the artists in residence and look at their studios and talk to them. We had the Met Opera come and sing an aria in our grand hall. It's a very grand space. It's an old ironworks factory, so it's very brick and wood, and it has a real quality. And we have astronomers in the garden, often just doing public viewing from our garden. And we have this big ambition, which is really very consuming, very exciting, and I think very impactful, to build New York City's first public observatory on the roof of Pioneer Works. And it's really a crazy ambition. Do you know Fitzcarraldo, the film by Werner Herzog, where he drags the steamboat?
Yeah.
So Fitzcarraldo drags a steamboat through the Amazon, blaring opera to bring culture deep into the Amazon. I feel like that's our Fitzcarraldo moment. We're trying to hoist this observatory onto the top of this building, and
That'd be amazing.
we're having as a centerpiece an antique instrument from the same era, the late 1800s. And it's fashioned very much after the dome here at Columbia, which is a private observatory. But it's where I first touched a telescope and learned how to use a telescope and to observe. And so very romantically, we're fashioning it in that style.
Wonderful. And anywhere else people can find you if they want to learn more about your work or read more about what you've
where
been doing?
am I? I guess I'm at Janna Levin on Twitter and Instagram.
Mm-hmm.
I'm there sometimes, not there all the time. And pioneerworks.org, you will see a lot of our events there. And we have a YouTube channel where our events are published. And our magazine, I really should have said this because I founded the magazine and launched it with Michael Jones, the managing editor, during COVID. And it's really a big outlet for us. It's called Pioneer Works Broadcast. You can also find that on the Pioneer Works website. But Broadcast is a really vibrant virtual magazine. We have a yearly print edition, but it's mostly virtual, and we cover everything in art, science, music, tech.
Okay.
So it's a real place for, even if you are not close enough to come to Brooklyn, you can check out how we're thinking about the world.
Yeah, that's very helpful. I'm sure lots of people will check that out. And thank you again, Janna. This was
Thanks so
wonderful.
much, David. It's
Yeah,
always
thank
fun
you.
to chat.
Absolutely. So that was my conversation with Professor Janna Levin. I hope you enjoyed it as much as I did. Black holes are just such incredibly mysterious, alluring, strange beasts. They seem like something that the universe should prohibit, and yet we have overwhelming evidence for their existence at this point. I think it's not a surprise that many of our greatest physicists, when first encountering the idea of black holes, were skeptical of them and didn't think they could be possible. In the same way that when we first encountered dark energy or dark matter, it seemed ridiculous that these things could be real, and yet now we have so much evidence that black holes are out there. In fact, a central building block to the universe itself, that we have to accept that the universe often just surprises us. What we think is not possible doesn't matter. The universe has its own mind almost about what it's going to do and how it's going to build its own architecture, its own structure. So amazing things. I think one of the most alluring and intriguing aspects of black holes is the way they force our theories of the large scale, such as general relativity, and the small scale, quantum theory, to confront each other. I think that is what gives me a bit of hope that we might one day find some kind of grand unified theory which could connect these two seemingly disparate ideas, disparate scales together, which of course has been something we've been trying to do for decades now in theoretical physics, to try and find that one beautiful, elegant theory which can marry gravity with the micro world, the quantum world. Black holes are perhaps the best possibility of us finding those bridges, those connections, such as the information paradox that we talked about earlier. But of course, one can't be talking about black holes without thinking about all the possibilities they open up. There's so much stuff actually we didn't even get into with Janna, such as the idea of using these things as essentially machines, right? We could actually turn black holes into engines for power through things like the Penrose process or the Halo drive, which we've done an episode on the Cool Worlds Lab. They're incredibly powerful intellectual beasts, right? They really force us to think about things in a completely different way and open the door to many strange and almost rule-breaking possibilities that we might be able to pursue. So black holes, I mean, what can you say? They're just amazing. So I'm so glad we live in the universe of black holes. I hope you enjoyed that conversation. We had another episode previously on here about black holes, and I plan to do many, many more in the future as well, because I don't think I'm ever going to get bored of this topic, and I don't think you will either. So if you enjoyed this episode, please do make sure you do all the things to keep up to date with our future episodes. So you can subscribe to the YouTube Cool Worlds podcast channel, which maybe if you're watching this, you're watching on right now, or you can catch this podcast on all of the platforms, iTunes, Spotify, all that kind of stuff. Make sure you hit it on there so it comes up in your recommendations. If you are not already, I hope you are. You can subscribe to the Cool Worlds main channel as well. And if you really want to be our super helper for the kind of content we produce here, the best way to do that is to head to the website coolworldslab.com/support. That's coolworldslab.com/support, where you become a donor to my research team, the Cool Worlds Lab. Now that by making that donation, it kind of just frees us up to make more of this content, right? Because it means we have to make less proposals for grant money because we're being supported by you guys directly. That allows us to pursue more ambitious and bold research ideas. And at the same time, it actually means it gives us more time to make this kind of content rather than worrying about writing 10 proposals where 9 out of 10 of them get rejected, which is the usual world of academia. So I'm incredibly grateful to all of you who support what we do here. And if you want to follow along with all of those cool worlders, that's the way to do it. coolworldslab.com/support. So thank you again for watching, and thank you to my guest, Janna Levin, and I'll see you all next time.